Here in the Tatard Galaxy, more than 400 million light-years from our galaxy, space is calm, imposing, with its share of color and mystery, but at the same time, in a galaxy far, far away, in a huge molecular cloud of more than 65 light-years in diameter, is a fragment, a size of 3 light-years. This fragment, nobody knows it yet, but it is this fragment which will be at the origin of our solar system. For the moment, everything is calm, but in the space of a few moments, in a luminous explosion, somewhere in this huge cloud appears a supernova. This shockwave causes the appearance of other supernova in the neighborhood of the fragment, and it is this shockwave which triggers the formation of our star, creating denser regions within the cloud to the point of initiating its collapse. This fragment, which represents a small portion of the cloud, by collapsing leads to the formation of a dense core of the size of 10,000 astronomical units. We call it the Presolar Nebula. Our Sun would have been formed near massive stars with short lifetimes, because they are the only ones that can form supernovas. It would therefore have appeared in a large region of massive star production, probably comparable to the Orion Nebula. The study of the structure of the Kuiper Belt and the unexpected material found there suggests that the Sun was formed among a set of stars grouped in a diameter of 6 to 19 light-years, in the whole representing 3,000 solar mass. After 535 million years, this cluster has completely disintegrated. Different simulations of our young Sun interacting with nearby stars during the first 100 million years of its life produce anomalous orbits. Such orbits are still observable today in the outer solar system, especially those of scattered objects. The Presolar Nebula, with a mass and composition similar to the present Sun, consisted of hydrogen, accompanied by helium and traces of lithium, forming about 98% of its mass. The remaining 2% of the mass represents the heavier elements, created by older generations of stars. At the end of their lives, these older stars had expelled the heavier elements into the interstellar medium and then were captured by the solar nebula. Because of conservation of angular momentum, the nebula rotated faster as it collapsed. As the materials within the nebula condensed, the frequency of collisions of the atoms that made them up increased, converting their kinetic energy into heat. The center, where most of the mass was collected, became increasingly hotter than the surrounding disk. Over a period of 100,000 years, the competing forces of gravity, gas pressure, magnetic fields, and rotation caused the nebula to contract and flatten into a rotating protoplanetary disk with a diameter of about 200 astronomical units, and forming a hot, dense protostar at its center. After 50 million years, the temperature and pressure at the core of the Sun became so high that its hydrogen began to fuse, creating an internal energy source that opposed gravitational contraction until hydrostatic equilibrium was reached. The Sun has just entered the first phase of its life, known as the main sequence. These stars derive their energy from the fusion of hydrogen into helium in their core. Even today, the Sun is a main sequence star. As the early solar system continued to evolve, it gradually moved away from its siblings in the original molecular cloud and continued to orbit alone around the center of the Milky Way. It is assumed that the various planets were formed on the basis of the solar nebula, a disc-shaped cloud of gas and dust, which was not directly engulfed in the formation of the Sun. The phenomenon, today retained by the scientific community, according to which the planets were formed, is called accretion. According to this process, the planets are born from dust grains of the accretion disk in orbit around the center protostar. Following direct contacts, these grains of a few hundred meters aggregate into blocks of several kilometers in diameter, which, in turn, collide with each other to form larger bodies of about 10 kilometers wide. They are called planetesimals. During the next few million years, these planetismals gradually increase in size by a few centimeters per year with new collisions. The inner solar system, that is to say, the region of the system at less than 4 astronomical units from the Sun, is too hot for volatile molecules such as water and methane to condense. Also, the planetismals that form there can only be made of chemical components with a high level of sublimation, such as iron, nickel, and aluminum or silicate rocks. These rocky bodies will become the telluric planets, which are Mercury, Venus, Earth, and Mars. As these chemical compounds are quite rare in the universe, corresponding to only 0.6% of the mass of the nebula, the telluric planets did not experience significant growth. 100,000 years after the formation of the Sun, the terrestrial embryo stops accumulating matter and reaches only 0.05 of the current terrestrial mass. But little by little, new collisions and the fusion of bodies of the size of quasi-planets will then allow the telluric planets to grow to their current sizes. When the telluric planets were formed, they remained immersed in a disk of gas and dust. The gas is partially supported by pressure mechanisms, and therefore does not orbit as fast as the planets around the Sun. The resistance induced by the medium causes a transfer of angular momentum. This phenomenon results in a progressive migration of the planets towards new orbits. But when the gas dissipates, the inner planets tend to slowly move closer to the Sun. This migration finally places the telluric planets on their current orbits. The gas giants, which are Jupiter, Saturn, Uranus, and Neptune, form further out beyond the ice line. This line designates the limit between the orbits of Mars and Jupiter, where the matter is cold enough for the volatile ice compounds to remain in a solid state. The ices that form the gas giants are more abundant than the metals and silicates that form the telluric planets. These colder temperatures allow the giants to become massive enough to eventually capture hydrogen and helium, which are the lightest but most abundant elements in the universe. Over more than 3 million years, the planetismals formed across the ice line accumulate up to more than 4 Earth masses. Today, the 4 gas giants account for almost 99% of all the mass orbiting the Sun. And it is not for nothing that Jupiter is just behind the ice line. This line accumulates large amounts of water by evaporation of ice. This evaporation creates a region of low pressure, which facilitates the acceleration of the particles in orbit at the border of this line and interrupts their movements towards the Sun. In fact, the ice line acts as a barrier that causes the rapid accumulation of material at about 5 astronomical units from the Sun. This excess of material melts into a large embryo of about 10 Earth masses, which then starts to grow rapidly by swallowing the hydrogen present in the surrounding disk. The embryo then reaches 150 Earth masses in only 1,000 years, until it reaches its nominal mass, 318 times that of the Earth. The significantly smaller mass of Saturn could be explained by the fact that it formed a few million years after Jupiter, when there was less gas available in its environment. Uranus and Neptune are supposed to have formed after Jupiter and Saturn, but since then, the powerful solar wind has blown away most of the material of the disk. These 2 planets have had the opportunity to accumulate only a small amount of hydrogen and helium, totaling no more than 1 Earth mass each. This is where the qualification of failed core of Uranus and Neptune comes from. Where the planets are currently located, it would have taken them about 100 million years to aggregate their cores. This means that Uranus and Neptune probably formed closer to the Sun, near Saturn, or perhaps even between Saturn and Jupiter, and later migrated outwards. After 10 million years, the solar wind of the young Sun would have eliminated all the gas and dust from the protoplanetary disk, blowing it into interstellar space, thus putting an end to the growth of planets. After this point, only planetismals remain. At the end of the epoch of planetary formation, the inner solar system was populated by 50 to 100 planetary embryos, ranging in size from 1 to 2 moons the largest of which was the protoplanet that would form Mars. Further growth was only possible because these bodies collided and merged, which took less than 100 million years. These objects would have interacted gravitationally with each other, with the orbits of one pulling on those of the other until they collided, merging and growing until the 4 telluric planets we know today had taken shape. One of these giant collisions is probably responsible for the formation of the Moon, while another would have removed the outer shell of the young Mercury. This model cannot explain how the initial orbits of the telluric protoplanets, which would have had to be highly eccentric to collide, produced the remarkably stable, near-circular orbits that the telluric planets have today. One hypothesis is that the telluric planets formed in a disk of gas that had not yet been expelled by the Sun. With time, the gravitational resistance of this residual gas would have limited the energy of the planets, smoothing their orbits. But such gas, if it had existed, would have prevented the telluric orbits from becoming eccentric to allow the fusion of protoplanets. Another hypothesis is that the gravitational drag did not occur between the planets and the residual gas, but between the planets and the remaining small bodies. As the larger bodies moved toward the crowd of smaller objects, the smaller objects, attracted by the gravity of the larger planets, formed a region of higher density, a gravitational wake, in the path of the larger objects. In doing so, the increased gravity of the wake put the larger objects into more regular orbits. The outer edge of the telluric region, between 2 and 4 astronomical units from the Sun, is called the asteroid belt. The original asteroid belt contained enough material to form 2 or 3 planets like Earth, and a large number of planetesimals formed there. As for the telluric planets, the planetesimals of this region later merged and formed 20 to 30 planetary embryos. But the history of the region was strongly influenced by Jupiter's gravity, which increased the speed of these planetesimals, causing them to break up during collisions with other bodies, rather than to aggregate. As Jupiter migrated inward, continuing its formation, the resonances would have swept away portions of the asteroid belt, disrupting the dynamics of the region. This action either drove the planetesimals to the periphery of the asteroid belt, or disturbed their inclinations and orbital eccentricities. Some of these massive embryos were ejected by Jupiter, while the others were able to migrate to the inner solar system and play a key role in the final accretion of telluric planets. During this period of primary reduction, the effects of giant planets and protoplanets left the asteroid belt with a total mass equivalent to less than 1% of that of the Earth, composed mainly of small planetesimals. There followed a period of giant impacts in the heart of the inner solar system, which probably played a role in the acquisition of the water currently present on Earth from the former asteroid belt. The water is too volatile to have been present during the formation of the Earth and must have arrived later from more distant and colder regions of the solar system. Water was probably brought by protoplanets and small planetesimals launched out of the asteroid belt by Jupiter. According to the nebula hypothesis, the ice giants, Uranus and Neptune, are in the, quote, wrong place. Indeed, they are located in a region of the nebula where the density is reduced and where the long duration of the orbits makes their formation unlikely. It is therefore thought that they formed in orbits close to those of Jupiter and Saturn, where more material was available. They would then have migrated towards the outside of the solar system over a period of several 100 million years. The migration of outer planets is also necessary to explain the existence and properties of the outermost regions of the solar system. Beyond Neptune, the solar system extends into the Kuiper belt, the scattered objects, and the Oort cloud. These 3 sparse populations of small, icy objects are thought to be the point of origin of most observed comets. At their distance from the Sun, accretion was too slow to allow planets to form before the solar nebula dispersed, and so the initial disk lacked the mass density to consolidate into a planet. The Kuiper belt lies between 30 and 55 astronomical units from the Sun, while further out, the dispersed disk extends more than 100 astronomical units. The Oort cloud starts at 50,000 astronomical units. Originally, the Kuiper Belt was much denser and closer to the Sun, with an outer edge at about 30 astronomical units. Its inner edge was just beyond the orbits of Uranus and Neptune, which were in turn much closer to the Sun, at about 15 astronomical units when they most likely formed. At that time, Neptune was closer to the Sun than Uranus. After the formation of the solar system, the orbits of all the gas giants continued to evolve slowly. They were then influenced by the interactions with the large number of remaining planetesimals. About 4 billion years ago, Jupiter and Saturn entered a 2-to-1 resonance. Saturn made 1 revolution around the Sun, while Jupiter made 2. This resonance created a gravitational pull that pushed the outer planets away. Neptune then passed the orbit of Uranus and plunged into the old Kuiper Belt. The planet dispersed most of the small objects present towards the interior, while it moved towards the exterior. These objects, sometimes planetesimals, then diverted the next planet they encountered in a similar fashion, shifting the orbits of the planets outward as they approached the Sun. This process continued until the planetesimals interacted with Jupiter. The immense gravity that the largest planet in the solar system exerted on them sent them into highly elliptical orbits. Some were even ejected out of the gravitational influence of the Sun. This process brought Jupiter closer to the Sun. These objects scattered by Jupiter on highly elliptical orbits today form the Oort cloud. The objects scattered on a less significant inclination by the migration of Neptune form the Kuiper Belt and the scattered disk. This scenario explains the low mass of the Kuiper Belt and the dispersed disk. Some of the scattered objects, notably Pluto, became gravitationally bound to the orbit of Neptune. In contrast to the outer planets, the inner Telluric planets would not have migrated significantly during the evolution of the solar system, because their orbits remained stable during the periods of the giant impacts. The gravitational perturbations resulting from the migration of the outer planets would have projected a large number of asteroids towards the inner solar system, depleting the asteroid belt until it reached the very low mass that we know today. This event could have initiated the Great Late Bombardment, which took place about 4 billion years ago. That is, 500 million years after the formation of the solar system. This period of massive bombardment lasted several hundred million years, and is still evidenced by the ancient craters still visible on the geologically dead bodies of the inner solar system, such as the Moon and Mercury. The oldest traces of life on Earth date back 3.8 billion years, almost immediately after the end of the Great Late Heavy Bombardment. Impacts would be ordinary, if not rare, events in the evolution of the solar system. They continue to occur, as illustrated by collisions such as that of comet Shoemaker-Levy 9 with Jupiter in 1994, or the meteor crater in Arizona. The accretion process is therefore incomplete and may still pose a threat to life on Earth. The evolution of the outer solar system also seems to have been influenced by nearby supernovas, and probably also by the crossing of interstellar clouds. The surfaces of the most distant solar system bodies would have experienced space weathering from solar winds, micrometeorites, and neutral components of the interstellar medium. Moons orbit most of the solar system's planets, as well as many other space bodies. Jupiter and Saturn have a large number of moons, such as Io, Europa, Ganymede, and Titan, which may have originated from disks around each giant planet in much the same way that the planets formed with the disk around the Sun. This origin is indicated by the large size of the moons and their proximity to their planet. These two properties combined cannot be accumulated on captured moons. On the other hand, the gaseous nature of the planets makes it impossible to create moons by debris resulting from collisions. The outer moons of gas giants tend to be small and have eccentric orbits with random inclinations. These are expected characteristics for captured objects. Most of these moons orbit in the opposite direction of the rotation of their associated planets. The largest irregular moon is the moon Triton around Neptune, which is believed to be a captured Kuiper Belt object. The moons of solid bodies were created by collisions and captures. The two small moons of Mars, Deimos and Phobos, would be captured asteroids. The Earth's moon would have been formed as a result of a single gigantic oblique collision where the impactor object, called Theia, would have had a mass and size comparable to 2 times that of the moon. The impact would have taken place a few tens of millions of years after the formation of the inner planets. The collision projected into orbit part of the mantle of Theia, which aggregated to form the moon. This giant impact was the last in a series of mergers that formed the Earth. Charon, Pluto's moon, could also have formed through a large collision. The Pluto-Charon and Earth-Moon pairs are the only ones in the solar system in which the mass of the satellite is greater than 1% that of the planet. The solar system travels around the Milky Way with a circular orbit approximately 30,000 light-years from the galactic center. It takes at least 220, maybe 250 million years to complete one revolution at a speed of 220 kilometers a second. At this rate, since its formation, the system has already made at least 20 revolutions. Some scientists have suggested that the path of the solar system through the galaxy is one of the factors explaining the periodic mass extinctions observed on Earth through the fossil record. During its orbits, the Sun experiences slight vertical oscillations that lead it to regularly cross the galactic plane. When it is outside the galactic plane, the influence of galactic tides is at its weakest. When it enters the galactic disk, which occurs every 20 to 25 million years, it returns under the much more significant influence of the galactic disk, which, according to some mathematical models, increases the flow of comets coming from the Oort cloud. This flow, then 4 times more intense, leads to a significant increase in the probability of a devastating impact. But other scientists note that the Sun is currently close to the galactic plane, and that the last great extinction event was 15 million years ago. Therefore, the vertical position of the Sun could not, by itself, explain these periodic extinctions. They then retain rather as a trigger the fact that the Sun crosses periodically the spiral arms of the galaxy. The spiral arms contain not only a great number of molecular clouds, but also a greater concentration of bright blue giants. While the cloud's gravity can interact and disrupt the Oort cloud, the shorter-lived blue giants can explode violently into supernovas. Astronomers believe that the solar system, as we know it, should not change until the Sun has fused all the hydrogen in its core into helium, beginning its evolution from the main sequence into the red giant phase. In the long run, the most significant changes in the solar system will come from the evolution and aging of the Sun. As it burns its fuel, it will increase the temperature by burning the remaining fuel even faster. The Sun will increase its brightness by 10% every billion years. In a billion years, the radiation emitted by the Sun will have increased and its habitable zone will have moved outward, making the Earth's surface too hot for liquid water to exist naturally. At that time, any form of terrestrial life will be impossible. Evaporation of water, a potential greenhouse gas, from the surface of the oceans could accelerate the temperature rise, which could end all life on Earth even faster. At this time, it is possible that the temperature of the surface of Mars could gradually rise. Carbon dioxide and water currently frozen under the Martian soil will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially providing a new island for life. In 3.5 billion years, conditions on the Earth's surface will be similar to those on Venus today. In about 5.4 billion years, the core of the Sun will have become hot enough to start hydrogen fusion in its upper layers. This will cause a colossal inflation of the star's surface, which will expand accordingly. At this point, it'll enter a new phase of its life cycle, known as a red giant. In 7.5 billion years, the Sun will extend over a radius of 1.2 astronomical units. That is 256 times its current size. At the apogee, it would have brightened its surface to reach a luminosity 2,700 times more than it is currently, and will be consequently much colder on the surface, approximately 5,252 degrees Fahrenheit. During this period of its life as a red giant, the sun will cause a solar wind, which will carry away approximately 33% of its mass. In the distant future, it is possible that Saturn's moon Titan could reach a surface temperature necessary to support life. As the sun expands, it should absorb the planets Mercury and, most likely, Venus. The fate of the Earth is less clear. As the sun envelops the current orbit of the Earth, it will have lost a third of its mass and gravitational pull, causing the orbits of each planet to expand considerably. Considering only this phenomenon, Venus and the Earth could probably escape incineration. Gradually, the hydrogen burning in the mantle surrounding the solar core will increase the mass of the core until it has reached about 45% of the current solar mass. At this point, the density and temperature will become so high that the fusion of helium into carbon will begin, generating a helium flash. The sun will then decrease from 250 to 11 times its current radius. Its luminosity also decreases from 3,000 to 54 times its current level. The sun will become a horizontal branch star, burning helium in its core in a stable way, the way it burns hydrogen today. The fusion period of helium will not exceed 100 million years. Eventually, it'll be forced to resort again to the reserve of hydrogen and helium in its outer layers and will expand a second time, turning into what is known as the asymptotic branch of the giants. At this point, its luminosity will increase again, reaching 2,090 times its current luminosity, and it will cool to about 5,792 degrees Fahrenheit. This phase will last about 30 million years, after which, over a period of 100,000 years, the outer layers of the sun will be gradually blown away by its impulse, ejecting a vast stream of matter into space and forming a halo poorly named a planetary nebula. The ejected matter will contain helium and carbon produced by solar nuclear reactions, continuing to enrich the interstellar medium with heavy elements for future generations of solar systems. It will be a relatively peaceful event, not at all like a supernova. An observer who could witness this event would have observed a massive acceleration of the solar wind speed, but not enough to completely destroy a planet. But the loss of mass of the star could cause chaos in the orbits of the surviving planets, eventually leading them to a collision, or even ejecting them completely from the solar system. After that, all that'll be left of the sun will be a white dwarf, an extraordinarily dense object, representing 54% of its original mass, all compacted into the volume of the Earth. Initially, this white dwarf could be 100 times more luminous than the present sun. It will be entirely made of degenerated carbon and oxygen, but will never reach a sufficient temperature to trigger the fusion of these elements. Thus, it will gradually cool down, becoming less and less luminous. When the sun will be dead, that is to say, that its heart will be exposed, its power of attraction on the bodies in orbit, like planets, comets, and asteroids, will have weakened because of its loss of mass in the previous stages. All the orbits of the remaining planets will expand. If Venus, Earth, and Mars still exist, their orbits will be about 1.4 astronomical units from Venus, 1.9 astronomical units for Earth, and 2.8 astronomical units for Mars. All planets will become dark, icy, and completely devoid of life. They will continue to orbit the sun, but their speed will be reduced because of the increased distance and reduced gravity of the sun. 2 billion years later, when the sun is cooled, the carbon and oxygen in the sun's core will freeze, with 90% of its remaining mass becoming a crystalline structure. Eventually, after thousands of billions of years more, the sun will cease to shine completely, becoming a black dwarf. Although the vast majority of galaxies in the observable universe are moving rapidly away from the Milky Way, the Andromeda Galaxy is heading towards us at a speed of 120 kilometers a second. In 2 billion years, Andromeda and the Milky Way are expected to collide, causing them both to warp. If this initial disruption takes place, astronomers put the chances of the solar system being pulled outside into the tail of the Milky Way at 12%, and the chances of it becoming gravitationally bound to Andromeda, and thus part of that galaxy, at 3%. After a new series of gravitational jolts, during which the probability of ejection from the solar system increases to 30%, a supermassive black hole will emerge. Finally, in about 7 billion years, the Milky Way and Andromeda will complete their merger into a gigantic elliptical galaxy. During the merger, the increased gravity will force the gas to concentrate in the center of the new galaxy in formation. This should lead to a period of intense star formation. The gas, by rushing into these newly formed black holes, will feed it, transforming it into an active galaxy. The violence of these interactions will probably push the solar system into the outer halo of the new galaxy, leaving it relatively unaffected by the radiation from these collisions. It would be wrong to believe that this collision can disrupt the orbits of planets within the solar system. While it is true that the gravity of passing stars can detach planets into interstellar space, the distance between stars are so great that the probability that the collision of the Milky Way and Andromeda will cause disruption to a given star system is negligible. Although the solar system as a whole may be affected by these events, the Sun and planets should not be disturbed. However, over time, the cumulative probability of a chance encounter with a star increases, and disturbance of the planets becomes virtually inevitable. Assuming that the Big Crunch or Big Rip scenario heralding the end of the universe does not occur, calculations indicate that the gravity of passing stars will have completely stripped the dead sun of its remaining planets within 1 million billion years. This point then marks the end of our solar system. Although the sun and planets may survive, the solar system as we understand it will cease to exist, leaving room for a new cycle in a new molecular cloud in a galaxy far, far away.